Yeah, like I said, thank you everyone for being here. There's some folks I haven't seen in a while, some faces, some names, and it really means a lot to me that you were able to make it out. So the first thing that I want to do is just talk about, like, what are we doing here? You know, I'm going to be talking about some kind of math for the next hour or so, but a little bit more specifically, everything in this talk is going to fall under the purview of algebraic combinatorics. So this is the fancy buzzword, and if you take nothing else away from the talk, at least you can say that you learned some fancy words. But what do they mean? Gosh, still doesn't like to go forward. So starting with the second word, combinatorics derives the name from combinations, and this is the theory of counting, roughly speaking. There's a lot written about exactly what constitutes combinatorics, but I don't think these things are so interesting if you're not already in the field, so theory of counting will be good enough for today. And then the other half, this algebraic, this is a different kind of algebra than like x plus 3 equals 4. There will certainly be that kind of algebra. But when mathematicians use this word, we often mean this as like a code for symmetry. So when I put these two things together, it means that I like to count things using symmetry. This is pretty abstract, so I'll get into an example fairly quickly. But one thing that I want you to keep your eye peeled for is that rotations are a particular kind of symmetry that are going to show up all of the time. They're very critical to the sorts of things that I think about. And yeah, I think you'll see that in the examples that we do. Before we get into this example, I want to make a small disclaimer, which is that we're going to be at this particular example for a while. So there's a couple reasons for this. There's a lot to say about it, but there's a lot to say about most things in the talk. The real reason why we're spending all this time here is because while this example is elementary, so you don't need any technical knowledge to understand it, it's not exactly simple. There are going to be a couple of moving parts, and so I want to make sure that we all sort of have some time to digest this thing. So what is it? This is going to start with a setup that I'm going to call the parking game. So we have 8 cars and we have 8 parking spots. And the goal is that we're going to try to get all of the cars to park. But if that were it, this is a very well-known problem, not quite as interesting as the sort of thing we're going to be thinking about. So we're going to add this extra rule, which is that we're going to give preferences to all of the cars. And then they're going to park according to their preferences in the following way. If their preferred spot is empty, they're just going to go straight there and park. They're going to go straight to their spot and see whether or not it's empty. If it is, then they park there. If not, then they get grumpy and they have to park as soon as possible. But the catch is that they can't turn around. Somehow the parking lot is too narrow. And so if there are no spots available to park in, then they're out of luck. We lose the game. And this is going to be the sort of things that we're trying to avoid. So more concretely, here's a list of preferences. And if we just start doing this operation, the first car, the red car, wants to park in spot 3, and they're the first car, so it's definitely empty. But the pink car also wants to park in spot 3. It's full, so they see that, and they're annoyed, but they go forward. They find that spot 4 is empty at least, so they park there. Going a little faster, right? The purple car is going to park in spot 7. The blue car is going to park in spot 1. And the teal car is going to park in spot 5 because it goes to 4, sees that it's full, and keeps going to the next empty spot. I want to pause on this one for a second because it was pretty obvious from the list that the pink car wasn't going to be able to park in spot 3 because somebody earlier in the list preferred that spot as well. But that's not true of the teal car. Nobody else in the list prefers spot 4, but just because of how things were arranged and people were forced to park, they weren't able to get their spot anyway. So there is a little bit of subtlety. Now the green car wants to park in spot 1, but can't. It parks in spot 2. the yellow car wants to park in spot 8, and it can. And then finally, the orange car wants to park in spot 2, but it's full, 3 is full, 4 is full, 5 is full. Finally, it finds a spot at number 6. This means we win the parking game. This collection of preferences is like a winning collection. And so we call such a collection a parking function. If we can get all of the cars to park, we have a parking function. Now, not every list of preferences is going to be a parking function, of course. If the last car had preferred spot 7, then it would have skipped over spot 6 in its haste to get to its preferred spot, and then can't park in 7, can't park in 8, and therefore isn't able to park at all. This is the sort of thing we're trying to avoid. And if we do manage to avoid it, again, we call this list of preferences a parking function. Like I said, it's a little bit of a complicated definition. So when you encounter complicated definitions like this, the first thing you want to ask is, are there any examples? And we know, because of the thing we just did, that yes, there is at least one parking function that we can write down. And so when you are a combinatorialist, the question that is always stitched on your heart, the next thing you want to know is how many? How many different preferences allow all the cars to park? How many parking functions are there? Ultimately, this is the question that we're going to get around to answering, but we're going to not attack it directly. Instead, we're going to make a little bit of a roundabout. In fact, we're going to literally make it into a roundabout. We're going to close up the end of the parking lot, add an extra spot for good measure. And this is what I'll call the circular parking game. So exactly the same rules, exactly the same win conditions, but the board setup is different. So it's not hard to see that in this new setup, we've made the problem a lot easier, because there's no way to fail anymore. You know, before you could get to the end and not have anywhere to park, but now it's a circle, right? So the only problem is, like, if you keep going around and all of the spots are taken, if we only have 8 cars, there are 9 spots, then that's never going to happen. Eventually, after enough rotations around, you'll be able to find a spot. So I claim, right, because of that, this is going to be a much, much easier question. How many different circular parking functions are there? And some fairly standard counting arguments here, right? Every car has 9 choices. And when you're making a bunch of independent choices, then you multiply the counts together. So it's 9 times 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 9, 9 to the 8th power. Just for reference, this number is about 43 million. So if you wondered, like, what's the theory involved in counting, this is sort of why we need some theory, because we're not going to sit here and go 1, 2, 3, 4 until we get to 43,046,721. We need some sort of way of doing things systematically. So you say, okay, well, you've changed the game and you've managed to make the question a lot easier, but that's kind of cheating, right? We need to still try to think about the original question. Now, you're all very smart people, like, you know that there's going to be some relationship here. I'm talking about them together, they kind of look the same. So exactly what the relationship is going to take, again, a second to explain. But importantly, the main thing that I want to emphasize is that we're going to do it by understanding the structure of the set of circular parking functions. If you're not, like, immersed in this kind of thinking, this might seem a little bit unintuitive, that we're going to try to gain information about the ordinary parking functions by trying to carefully understand what's going on for these related but not obviously so objects. You'll see how it works out in the end, but I just want to point out that this is a sort of technique that shows up all of the time. It's not so specific to this problem. So here I've drawn the circular parking lot again. I've put in the the cars, this is the example that was not a parking function from before. It is a circular parking function, of course, because any list of preferences will be. And the first thing that I want you to notice is that one of the spots is empty. Spot 6 is empty. It's easy to see that's going to happen all the time, right? If you only have 8 cars, but you have 9 spots, and everybody is going to be able to park, then of course, 8 minus 9 minus 8 is 1. And so we're going to have exactly 1 spot left empty. That's going to be the critical thing for us. We're going to play around with that spot. In particular, if I change the circular parking function, it's going to change which spot is empty. And the question that I want to ask and answer is there any way that we can change the circular parking function in a way that gives us control on what happens to that empty spot? So here's an idea. Subtract 1 from all of the preferences. Now, this requires a little bit of interpretation, right? What 1 minus 1 is 0, and 0 doesn't show up in the list. When I say subtract 1, I'm really thinking about rotating counterclockwise. I think that's the right way. And so, or equivalently, I'm thinking about 9 as being 0. If somebody's preference is 0, then I'm just going to relabel it as 9. And that, unsurprisingly, because all of the preferences got rotated 1 counterclockwise, that's going to rotate the empty spot 1 counterclockwise. And we can keep playing this game, right? We can keep rotating it around. And you can do that, 9 different times. You're going to get 9 different circular parking functions. And there's exactly 1 choice that's going to put the empty spot at spot 9. So why am I making a deal about that? Well, what do we know if the empty spot is at 9? Certainly we know that nobody preferred it, because if they had, either they would have parked there or somebody earlier in the list would have. But because 9 is the last spot in this ordering that we've given it has a special property that others don't, which is that if it's empty, it means that not only did nobody choose it, but also nobody drove past it, because there are no later spots that they might have preferred and like hastily driven past it to try to get. So in other words, we could just take a pair of scissors, right, and snip the parking lot at spot 9, and we would end up with a straight parking lot, sort of unroll it, with only 8 spots, and all of the cars would be able to park because nobody drove off the end. So somehow we don't need the circularity when the empty spot is at 9. The converse is also true. If you start with an ordinary parking function, then 9 is going to be the empty spot because just follow the same logic backwards. So back to our original question, how many different preferences allow all the cars to park? We're going to use the answer for the circular parking functions, and we just get to divide by 9 because we're thinking about which spot is empty. Of the 9 possibilities, when we rotate around, exactly one of them is going to work. There are 9 times as many circular parking functions as there are parking functions, and this ends up being the count for the number of parking functions. Again, just for reference, this is a phone number, right? It's some number just shy of 4.8 million. And you can sort of see that it's not so useful really to think about these numbers written out in decimal notation unless you're, except just to get a very rough estimate of like how big they are. Really this structural answer on the first line is a much more useful thing. Now, of course, I've used 8, but I didn't have to use 8. We could make this argument in general. If you have n cars to start out with, then you have n plus 1 raised to the power n minus 1. You should think about that as n plus 1 to the n divided by n plus 1. parking functions with. And so we have an answer, but the thing that I want to emphasize to sort of round this out is that I'm more interested in what happened in the middle. Just as a reminder, this is sort of putting it all down a little bit more carefully. We knew they had an empty spot. We moved the spot around to get to n+1 using this rotation. And then that guarantees that we get parking functions. And all of this information is compressed into, all of these ideas are compressed into this very like compact notation. This is something that mathematics is annoyingly good at. It's taking very big ideas and making them look very small. And so this is something that's going to show up a bunch. This like division symbol, we call this a quotient. And I'm not going to get too deep into exactly why these are the symbols we want to write down, but you can sort of see the answer showing up there. There's like an n+1 at the end, and there's like so that's like representing the circular parking functions in the numerator. And then we're thinking about some of them as being unnecessary or being the same is often the way that we describe that as well. And the denominator tells us how we think about things as the same. So this is going to conclude our conversation about parking functions until the very end of the talk. I want to go on to another example, which is in some sense simpler, but we're going to sort of go with that story all the way from right at the beginning to the brand new results that are in my thesis. So what are we doing? We have a string and beads. We're going to put the beads onto the string, and we are allowed to do any order we want. So not a lot of fanciness going on as there was in the parking function situation. And the beads have different colors. Even though you probably can tell the difference between, the three blue beads because I can't draw very well. Well, I'm thinking about those as all being indistinguishable. Like I shouldn't be able to tell the difference between. So these are the sorts of objects that we're looking at here. Now, one way to think about this is to put all of the beads into like a pile. But for our purposes, it's going to be more useful to start with them already lined up so that we can think about the objects that we actually care about, these beaded strings, as being just sort of a rearrangement of the starting line. So I'm going to tell you how to count these things without giving the precise answer. There's a very, not very straightforward, but there's a reasonably straightforward way of taking the thing that I will show you and converting it into a formula. But for me, again, the formulas are not so important. So what we have here is I have labeled the beads. And so now I can tell all of them apart. So I want to think about arranging these 11 beads on the string. And the collection of all ways to do that, I'm going to call S sub 11. So not everything in S sub 11 is a different beaded string, because of course, I'm not supposed to be able to tell the red beads apart. I could when they're labeled, but if I take off the labels, then that's the thing that I actually want to count. And so again, you see this quotient coming up, because we're trying to think about some of these things as being the same. And you see what's going on here. S5 means we're thinking about all of the red beads as being the same, or we're thinking about all of the possible ways to rearrange the red beads. And because they're in the denominator, that's why we're thinking about this. Similarly, S3 is the way to rearrange blue beads. S2 is the way to rearrange the green beads. And S1, not very interesting, but the number of ways to rearrange the white bead. But earlier, I told you that there was going to be rotations all of the time in this topic. And there's not a rotation here. So I'm going to introduce one. I'm going to tie the two ends of the string together into a nexus. So a necklace is just right. It's just an arrangement of beads on the circle, and we can get it from the beaded strings, which means that we're going to be able to get this as yet another quotient of the STR thing. Now, I have to apologize. I'm writing it in this way for the folks who are more technically inclined. I really want to quotient this thing out on the left. There is a reason for that, but it's not actually that important. It's pretty pedantic for our purposes here. But if you're worrying, like if you sort of have an idea about what's going on under the hood and you're worried about some definitions making sense later, this is the thing that fixes it. Okay. But yeah, not surprising that we're seeing this quotient show up because we're thinking about these rotations as being. Okay, so now we're going to go off the rails just a little bit. There's a certain rational function that you can associate to all of these necklaces, not the individual necklaces, but the collection of all necklaces when you fix the number of colors. So here's the definition. It's not terribly important. I'm not going to have a lot to say about Q analogs in this talk in general, but one thing that I want to emphasize, like the reason why it's on this slide at all is because I want you to see that this is something that I can plug into a computer, right? There's not some fancy like choices that we're making or like tricky procedures we have to follow. It's all just algebra. Now I do want to do an example, so I have to show you what at least one of these things looks like. And this is misleading in some ways, but it's going to work for us. This C4-3, so I'm thinking about 4 red beans and 3 blue beans. This rational function that I'm associating to it is in fact a polynomial, which is 1 plus q squared, q cubed, q to the 4th, and q to the 6th. I knew it was going to be a polynomial from the general theory because 4 and 3 don't have any common divisors. That's what that GCD alpha means. The only number that divides both of them is 1. So what am I going to do with this? Well, first I will say, yeah, I said I wasn't going to say anything. I will say very briefly why you might think this is a natural thing to associate to this collection. So if you write out all of the necklaces with 4 pink beads and 3 blue beads, then you'll see that there are exactly 5. And you might say like, oh no, I think I can draw another one. You probably can, but if you do rotation, you'll see that your picture is the same as one of them on this list. So one of the reasons why we might think that this polynomial is a good thing to associate to this collection is because when we plug in q equals 1, then all of the exponents don't really matter. 1 to the 4th is just 1 again. And so we're just adding up 1 a bunch of times, maybe with some coefficients if they had happened to show up. And in the end, we get 5. It's not a coincidence that 5 is the same as the number of necklaces in this collection. That's one of the things that we want from a Q analog. So I want to tell you about another way in which this Q analog tells you something about this set. And that story is going to start with this bit of notation. So what this tau 1, 2, 4, 3, 6, 5, 7 is doing for us is it's going to tell us how to rearrange beads in these necklaces. Now, I've chosen an ordering on the beads. It's arbitrary, but I'm just picking one that's consistent, and we'll use it to understand what we're doing here. So what is tau telling us? Like, how is tau telling us how we're rearranging things? So I want you to focus for now on just the far left picture. this tau is composed of 3 parts. It's the 124, which I've colored blue, 365 that I've colored orange, and then this red 7. And what that means is that we're going to take the bead in position 1. So this is 124. It tells us we take the bead in position 1, we move it to position 2. We take the bead in position 2, or that used to be in position 2, and we move it to position 4. And then 4 closed parentheses means that we go back to the beginning. For the bead that used to be in position 4 is now going up to position 4. Similarly, 365 means that we do that little rotation, and then 7 by itself means that it doesn't. So I wrote them out in full detail on the things on the side. For the 3 in the middle, I only wrote out the blue ones because you can see that the orange arrows are actually just going to send red beads to red beads, and the red arrow is going to send the 7th bead to itself. So they're not actually going to do anything. We're still, or they're not going to visually do anything. We're still thinking about them as happening, but to sort of see how this thing works, it's not going to make any difference on what we see. All right. So when we do that, we can find out that tau acts on the whole collection. Right? When you make these movements, what happens, which necklaces do each necklace go to? That's what I've tried to indicate with these blue arrows. And you might be a little bit confused about the things on the right and the left, because it sure looks like there's things are moving around a little bit too much. But again, this is the fault of the rotation. So I've done literally what you see when you do the blue, orange, and red arrows down in that lower section. But then if I rotate, for example, the thing on the left, I rotate it 2 counterclockwise, then that's going to get us back to the necklace we started with. Since we don't think about necklaces as being different, they only differ by rotation, then this is in fact the same necklace. So tau does nothing. All right, so this is how tau acts on this space. And now here's where it gets a little bit strange. If you plug in cube root of unity, right? So this is a genuine complex number, 1/2 plus square root of 3 over 2 times I. You plug this into the polynomial and just like go through all of the arithmetic. What you find is that you get the number 2. This number is not only a real number, which is not at all obvious. You just plug a random complex number into a polynomial, generally that's not going to happen. You're going to get some imaginary component. But it's also an integer. It's also a positive integer. It's also a positive integer that counts something. And the thing that it counts is related to the collection of necklaces, the thing we were taking the Q analog of. So this is really just miraculous, right? There's no reason to expect that anything like this should happen. But indeed, this is not an accident. This is one of the results from my thesis. And for the folks who are seeing this stuff for the first time, I don't want to overstate my contribution here. The idea of plugging in these complex numbers into Q analogs was something that's been floating around, depending on who you ask, like maybe for 50 years or so, but certainly for the last 17 years. There was a paper by my advisor and 2 other professors at the University of Minnesota on this thing called the cyclic sitting phenomenon. And this is an example of that. But my contribution is to observe that this paradigm that this is a thing you can do, and the question is, does it work? And my contribution is to show that for necklaces, it does indeed work. Now, there are some conditions here, right? And so I think I'm not going to say too much about them curious, ask me at the end. But this is sort of the flavor of. So I'm looking at my time, and it seems like we're doing okay. So maybe if there are questions at this point, things are going to sort of go off the rails a little bit in the technicalities department. So this would be a great time to unmute yourself or type something in chat.
Just because I'm curious, so you said that there's this thing for complex numbers. Are there things like this for quaternions?
Yeah, that is something that I haven't thought about. But I mean, off the cuff, it's possible that maybe if you were thinking about not a cyclic action, but maybe some other groups, you could maybe imagine those sorts of things would show up, just because like you have more freedom in terms of what things square to one, or not square, but in general. And so yeah, I don't know of anything like that, but it's an idea. Maybe before I get back into it, I realize I have some things on screen. Can you see the titles of the slides? Are those covered up by like windows, random windows? Okay. Thank you. All right, so we're going to go back to parking functions. So at the end, I told you that we had this way of thinking about parking functions as this quotient. And I'm going to do a little bit of maneuvering on this quotient. The first thing that I'll do is use this construction called a tensor product to get the subscripts out of there, right? To move that into sort of its own little world. And even if you don't know what the tensor product is, it maybe is sort of believable that you could do something like this, because that denominator there is really supposed to be thinking about rotations. And the n+1 is really only used to say like how big the lot is. So you could still imagine doing rotations if you just made the lot different sizes. Right? So maybe these two things aren't exactly related to each other and could be split apart. And indeed, that's true. A slightly more subtle thing here is sort of the reason why I wanted to do this is because this is the same thing as Q tensor Zn+1, where Q is this construction. If you are familiar with root systems, this is the root lattice for type A. If not, it's just some object that people tend to care about. And so writing things in this way makes it a little more interesting. Might make somebody's ears perk up who's in the field somewhere else. And so that's a thing. Oh, yeah, I should say before moving on too far, everything that I'm doing here will in fact work for Weil groups, but I'm going to be focusing on the other side of the tensor product here. That n+1, like I said, isn't doing a lot for us. It's not doing nothing, it turns out. That last equality is requiring something, but what it's requiring is that over in Zn+1, the operation of multiplication by n needs to be an invertible operator in order for this equality to be true. So making that less fancy, that happens whenever the subscript there is coprime, right? Again, has no factors in common with n. And in fact, that happens more generally if you have any abelian group of the appropriate order, right? Also coprime too. So this is just some construction, and everything else is just sort of motivating why I'm thinking about these as like parking functions. But it's in principle just some abstract construction. Repeating the definition again, literally nothing has changed. It's just at the top of the slide. The reason why I was thinking about this is yeah, I'll say a little bit more about the motivation later, but when I came to this question, I really wanted to understand if we all sat here and picked out our favorite abelian groups of order B, and we all named the appropriate parking spaces. How is there any way to like quantify how different they would be? And it turns out that, yeah, actually there is. They're not different. At least they're not different as SN representations. So there is maybe a subtlety here, right? They're not maybe isomorphic as permutation SN representations. So this is in particular approved by character computation, so it's not strong enough to get there. Interestingly, I don't know any counterexamples. It seems, well, I don't want to say it seems like, but at least in rank 2, it's true that there are, that these things are actually isomorphic and in that stronger sense, but that's definitely a thing that could be interested in continuing to look at. In any case, this is the only, we're only going to need it at this level for what we're going to use it for. And that involves a relationship to a different notion of parking spaces, which at the beginning is just going to look completely different. So this is the most technical slide of the talk. We want to look at the irreducible reflection representation of the symmetric group. And I just put this equation there at the beginning to say, like, if you were comfy with Q, right, you can think about this as instead of an abelian group or as a lattice, you can think about it as a vector space, and that's really the object going on here. So then if we do some very standard things, then we can start thinking about polynomials on that irreducible reflection representation. And what Heyman proved in '94 is that there's a certain very special these certain very special collections of polynomials that have maybe more nice properties than you would expect is possible. So the thing that we're doing here is we're looking for copies of the irreducible, or the dual of the irreducible reflection representation up in some higher degree, so up in degree B. But we not only want that, we want to be able to find a basis for that representation such that these things form a homogeneous system of parameters, which is some construction, or which is some technical property. The purpose of that property, though, is really to say that when we do this quotient, that the thing that we're going to get is finite dimensional. So the fact that these thetas carry the irreducible reflection representation, live in constant degree, gives you that the quotient is a graded SN representation. The fact that it's finite dimensional comes from this extra property of homogeneous system of parameters. And in fact, you can take this to be the definition that such quotients are finite dimensional, but let me not say too much about that. So again, this thing doesn't really seem to be anything, right? It's just some construction that you can play around with. But in fact, this theorem, I have a feeling that Heyman knew it, but as far as I can tell, he didn't write it down, so I'm attributing it to Summers, which is that this construction that he made, so this, which I'll refer to as Heyman's parking space, is in fact the same as the sorts of parking spaces that we were thinking about before. Because this is a purely algebraic construction, you do have to do the linearization. You have to throw that C on there in order to even make sense of what this isomorphism could mean, but it does work. Now, the advantage on there are advantages to both sides. The advantage on the left-hand side is that it's graded, right? It comes from this construction that sort of have a lot of algebraic tools to play around with. The advantage on the right-hand side is that if you throw away the C, this thing is linear. This thing is an action, right? It's a permutation representation. And so we can start to ask about like how you might transfer that kind of structure over, between the two sides. So I'm going to be interested in thinking about something that happens over on Heyman's side and moving it over to the more classical side. And exactly the thing that I want to do is I want to observe this really trivial observation that you can just multiply things by numbers. And if those numbers are roots of unity, then that is an action of the cyclic group. Okay, this is right. I was worried about a typo there, but I think we're good. Yes, so this is an action of the cyclic group, and it also commutes linearity. So of course, you can't stop me from just doing the same thing over on the ordinary parking space side, but that's not so satisfying because the thing originally came from a permutation representation. And so we'd like to know if there's like literally something you can do to the parking functions, right? And repeat that cyclic representation over there. So this is a genuine question. I do not know the answer to it, but I know the answer sometimes. And that in the case where B is a power of a prime, I have a favorite abelian group, which is the additive group of finite field. And that has a natural notion of a cyclic representation of the correct order because multiplication, the multiplicative group of the field is cyclic. So we just multiply on the right tensor factor, sorry, the right tensor factor by this field multiplication. And it turns out that this ends up working. Like not only can you define this action, but in fact, it ends up being isomorphic to the Heyman's parking space. I want to emphasize that there are sort of weaker cyclic actions that you could like think to do if you had other abelian groups sitting over there, but some of them just don't work. Like they don't end up being isomorphic. In general, like if you are going to ask me for a full order Q-1 action, I don't know how to do that in any other case except for the finite fields. So the reason why I needed to go all the way to abelian groups is because that allows me to even just define this cyclic action. And then from there, we're able to prove that it works out. Okay, so I want to conclude by saying a few words about what's coming up. So very briefly, just saying some words from the experts. I want to try to generalize these results from the symmetric group to complex reflection groups. As I noted before, the parking theorem works all the way up to Weil generality. Yeah, we have some ideas about what might happen for more general groups, like how to make the grammar work out, but not a lot of data for me to like put a conjecture out there right now. We also, like I said, there were those technical conditions in the necklace theorem. Some of them are definitely like required. There's no way to get rid of them. But the cycle type conditions on tau seem like fake news to me. Like there are definitely other tau that will work, but exactly understanding which of those they are doesn't seem to be so easy. And then the last thing is I'd like to resolve a certain unimodality conjecture. And I think I'm gonna skip over this motivation. This is the last slide of the talk. And just write down the conjecture. So this comes from a theorem that is also my thesis. And what this theorem says is that there's this sort of parity unimodality property. Somehow we would like the polynomials their coefficients to go up and then go down, but they don't. And so, but somehow if you split them apart by parity, then they are able to do that, which is like a very strange fact. Now, I only know that this is true when I have this special form of alpha, right? A minus k, b minus k, k, and the a and b have no factors in common. So that is good enough to cover the Catalan case. In general, this is the rational Schroeder generality, but all of the data that we have suggests that this unimodality property actually works for any alpha. This appears to be really difficult. Certainly, if you were going to try to extend my methods to all alpha, that seems, I mean, plausible, but very hard. This theorem up at the top is proven by some sort of analysis of the representation theory of a certain module over the rational Schrödinger algebra, which is exactly as technical as it sounds. So if there were easier ideas that could be used, like that would be very cool. Or if somehow you could extend that to more exotic algebras and get all alphas, that would also be very interesting. In any case, I just want to say thank you if you've made it this far. I'm very honored to be able to have written a small part of this story, but I wanted to conclude with sort of what we don't know, because that's really the honest picture here. It's a living narrative, and I hope that I can play some small part in continuing to tell that narrative going forward. But in any case, I'm really excited to see what comes.
Okay. Thank you, Eric. Are there any questions? Any questions?
I have a question for Eric. Okay, so you mentioned a couple of times, Eric, that you have places where you have an idea of something that might be true, but not necessarily enough data to put a conjecture out there. Are you in the process of producing data?
So on the cyclic sieving side, that was a project that I've been putting on hold for a while. So the answer is, in theory, yes, but it hasn't really happened. On the parking space side, like I'm sort of actively working, especially to think about like appropriate replacements for the root lattice for more general reflection groups.
And then as a follow-up question, so you're talking, these like this root lattice statement seems like a structural thing about replacing. Are you doing, I'm wondering sort of like, you have this fake news comment from Tao. Are you like computing examples in Maple or something to figure out if there's a reasonable replacement in that way?
Yeah, sorry, that's what I meant by the data that in principle I'm collecting. If you had something else in mind for the sitting, then okay. Yeah, it probably will be with Gap.
Okay, I have a question. There's this notion of G function of G. Have you tried to see somehow generalize from complete graph to more general graphs? Like graphs which have certain symmetry.
No, to answer the question, I haven't. I guess one comment that I would make sort of in that direction is that the proof of the complete graph case is yeah, like I've only thought about it in a type dependent way, right? So I don't have a uniform proof of these results. And so like that's sort of the direction that I've been trying to like think about understanding like what's going on under the hood. But yeah, thinking about this other direction of generalization is not something that I've given any attention to, but it's a good idea.
Eric, I'm sorry if I missed this
Awesome.
earlier, but these the parking functions. Are there places where these tend to show up? And again, sorry if you've already talked about this.
Yeah. Yes. To answer the question, these are. So it's I think about like parking functions through the parking spaces, and so like I have a very biased view in that sense. But I know that people think about like the parking functions themselves, and there's like been this recent work on S parking functions, if I'm getting the name right.
On what?
S parking functions. Galen, am I getting that right?
Like signature parking functions?
Signature, yes.
Okay.
Yeah, and so this is a thing. They show up in there's a lot of representation theory of the symmetric group stuff that you can say here, especially about like McDonald polynomials. Like they show up in that theory as well. On a different note, which I think will be of general interest, even though it may not have been what you were asking about, the reason why parking functions were originally studied actually was from queuing theory, from statistics, and also from computer science resolving hash functions. From what I understand, I don't know very much about the statistics story, but from what I understand, the computer science, this way of resolving hash functions is still pretty efficient and like actually used in practice. So pretty cool.
Thanks.
Eric, wonderful presentation, by the way. My question is going to be about, there was this one part of the talk where you showed this equation where you plug in this complex number and then we get 2 back, which is a fairly surprising result. My question is, and I think this is where you were counting necklaces and the rotations of them. With that complex number, I think it was like e to the 2 pi I over m. Is that, so when you plug in that complex number, could you use Euler's identity to remove the complex part? And that's why we can just put in a complex number and get a real number back? Or is there some trickery to this that we can't really see yet?
Yeah, so it's definitely, that's, Euler's identity is like sort of at the basis of all of it, to be sure. The way that I think about how these computations look when I sit down and like, really do the plugging in is that, is this business about how if you have like, if you sum up all 3 cube roots of unity, sorry, it should be that way, right? Then they sum up to 0 because they're on the vertices of an equilateral triangle. And so you can see that sort of cancellation like shows up and is really responsible for getting rid of the complex business. So in this example, you can see that q squared, q cubed, and q to the 4th are 3 consecutive cube roots of unity. So they cancel. And then 1 plus q to the 6th is 1 squared. So that's where the 2 comes from here.
Gotcha. Okay. I think that makes more sense. Yeah. Thank you.
Yeah, it is totally shocking. But it's a good miracle.